Okay. And then oh, I need to share my screen, don't I? Okay. Okay. Good. All right. So just um, to recap from last time so that we can continue. What I'm trying to do here also, that those of you that are on Zoom so that you can hear me, I brought the computer a little closer, as close as I can get. In case I move a little bit, you can still hear me. We'll see how it goes with the wires and everything. Okay, so define chromatography. We talked a lot about it, but it's very simple. We can define it in a few words. So who wants to, okay? Can you say that louder? Because oh, let me remove my mask. I am wearing the face shield. Okay. Yes, Giorgino said that it is basically separation of a mixture. So when we have components within a mixture, chromatography allows us to separate them. And then this is the first requirement before identification or detection, identification, and quantification. So great, that's the simple definition of chromatography. So what's the difference between stationary phase and a mobile phase, and what's the function of each? Dan? Exactly, Dan said it in a very simplified way, that the stationary phase is where our components of interest are attracted to and interact with, and it's not moving, it is stationary, it's on the word. And then the mobile phase is the moving phase where the components are pushed along the stationary phase and then leave whatever is a column, or if it is a paper or a thin layer chromatography, basically moving them along the way and out. Okay, list 3 types of chromatography. So if you remember last time I said, if in an exam or a quiz, I asked you what type of chromatography would you rather use to separate caffeine from different phenolic compounds in your sample, or to separate flavor components, or to separate fatty acids. So what would you tell me, Sam? Yes, exactly. So Sam said, well, we can go either with a gas chromatography or a liquid chromatography. And then the third one was supercritical fluid chromatography. So yes, these are the different types. You will learn today different phases and different modes of separation. So when I ask you about a specific mode of separation, then you would state what the mode of separation is: normal phase, reverse phase, etc. And we'll talk about that later. What is the form of mobile phase in GC, and what is the form of the stationary phase in GC? So gas chromatography, are we getting any? Let me see if I can, like last time, go and look at the chat box here. Yeah, and bring it up. Okay, so the mobile phase in gas chromatography is gas. Okay, so usually when we say gas chromatography or liquid chromatography, we're referring to the mobile phase. Okay, so when we say gas chromatography, your mobile phase is gas. And then the stationary phase in the olden times, it was solid. But most recent gas chromatography column, they would have the solid, but they would have a layer of a liquid. So it hence the name gas liquid chromatography. Sometimes you would hear that. But it is, the stationary phase is either solid or sometimes the solid coated with a liquid phase. Okay, same question for partition. So what's the partition chromatography mobile phase and stationary phase? What would it be in partition chromatography? Liquid, liquid, yes. So in partition chromatography, so your solute is partitioning between two liquid phases. The stationary phase is liquid and the mobile phase is liquid. In adsorption chromatography, in adsorption liquid chromatography, liquid solid. Thank you, Jean. So yes, liquid solid. So your mobile phase is liquid and your molecules or compounds of interest are adsorbing to a solid matrix or the stationary phase. So what is partition coefficient? When you hear the partition coefficient, what does it mean to you? It's a constant. In partition chromatography, it is a constant. What is it? When we hear the word partition, what is partitioning and what is partition coefficient? Yes, Chrissy? Exactly. So it is the partitioning of the solute or the component of interest. I would rather have it, I know in the slides it says partition in the stationary phase over partition on the mobile phase. It can go both ways, but it can be also partitioning between the mobile phase over the stationary phase. So it's the ratio of the concentration at any time point in equilibrium between the mobile phase and the stationary phase. What are some applications of chromatography? I know we listed quite a few last time. So if you want to throw in a few applications, either for GC or HPLC. Anybody? Sam? Identifying adulterants. There's so many different adulterants. Depending on the type of the adulterants, they could be polar. Mostly if they're polar, we use liquid chromatography. If they are non-polar and they can volatilize and they're thermally stable, we can use GC. Other than that, we listed quite a few. Let's see what we're getting here. Compositional analysis, antioxidants, yes, compositional analysis like fatty acid composition, amino acid composition, sugars, different types of sugars, if we're looking for identifying or quantifying different types of sugars in a sample. Vitamins, exactly. We have a long list, and the entire semester, when we start covering different chapters, we'll give examples and application of how we use GC or HPLC for the determination of these different components. Okay, great. So we can move along here. So I'm going to go, yes, Georgina. Yeah, mode of separation is basically when I ask about mode of separation, I'm looking at the physical chemical characteristics that causes the separation. And today I'm going to cover all of that. So, or at least introduction to that. So are they separating based on charge? So are we going to do ion exchange chromatography? Or are they separated based on polarity? So normal phase versus reversed phase. Are they separating based on hydrophobicity, like in hydrophobic interaction chromatography? So then when we talk about mode of separation, I want you to be more specific. Within HPLC, what's the mode of separation, for example? So what I'll be covering now, it's introduction to chromatography, but mostly liquid chromatography. On Friday, Gary is going to talk about specifically gas chromatography. So liquid chromatography is going to take me potentially this lecture and 2 other lectures to complete it, but it's mostly focused on liquid chromatography. So under liquid chromatography, if you remember when we talked about the different formats, we had planar chromatography and column chromatography. So for planar chromatography, there's the paper chromatography and thin layer chromatography. They're mostly qualitative. You can do semi-quantification by looking at the intensity of the spots, but it's mostly qualitative to see what you have in your sample, if it's present, not present, distribution of the different components. And paper chromatography, it's used, but it's not very commonly used anymore. Thin layer chromatography is used a little bit more, but mostly when you do screening. But then when you want to do real quantification and identification type of work, you want to do column chromatography. So in paper chromatography, and I'm sure you must have seen it or done it in organic chemistry potentially labs, yes. Okay, so in paper chromatography, from the name, it's paper, you use paper, and it's made of cellulose. And the cellulose serves as a support, only a support. So what you would do is you would have a liquid phase that would the cellulose absorb it or absorb that liquid phase. So basically you would have water as your stationary phase on the paper. So the paper, you wet it with water, and now your water is your stationary phase. So you take that wet paper then, and then you would spot on that paper your different samples. So sometimes you would have a standard, and then you would spot the rest of the samples on that paper. Okay, and then you would put it in a chamber, we call it development chamber. And then in that chamber at the bottom there, you would have another liquid that is immiscible with water. So hexane, heptane, ethyl ether. So they're immiscible with water. In this case, you have a polar stationary phase and a nonpolar mobile phase, which makes your mode of separation normal phase. Okay. And then you keep it in this chamber, so your paper is immersed at the bottom in that immiscible solvent, and you leave it there for a certain period of time, and then your different components move along with the solvent. So they go in ascending direction, and they go up, that is, and they start separating based on differences in their polarity. So basically, in this example here, let's say we are looking at amino acids, different amino acids. You spot them, and then you spray with ninhydrin. So ninhydrin basically is a reagent that will react with amino acids and give you different colors so you can actually see them. And then you will see the spots at the end when at the end of the development, when the solvent reaches the top of the paper, you stop it and then you look at your spots. The spots that move the least, so these at the bottom, that move the least, do they like the water or do they dislike the water? Would you think they're polar or non-polar? Remember, your solvent that is moving up is the immiscible solvent, the organic solvent, the non-polar solvent. And the water is impregnated all over your paper. So the spots that are at the bottom, do you think they're polar or non-polar, Dan? Huh? Polar. Yes, they want to stay with the water. They don't want to run away from water, and they don't want to run with the organic solvent. So those that would move further away from the start point, they're moving along with the organic phase. These are the less polar, relatively less polar. So one way of visualizing, depending on the different components that you are trying to separate, one way for amino acid is spraying with a reagent that will give you color like ninhydrin. Like sucrose and glucose here, the example, they are colorless, so you can visualize them by radiography or auto radiography, radioactive element. You can do 2D separation, and really you'll hear that multiple times throughout the semester, two-dimensional separation. You can do that with paper chromatography, you can do it with thin layer chromatography, you can do it with actual liquid chromatography, where you have different modes of separation, first mode and the second mode. And then you can do it with gel electrophoresis. So you can always try to separate with two-dimensional separation. What does it entail? So basically you start with your paper, it's impregnated with water, and then you put your spots and then you develop. Then you see spots that are not very well separated. So in your sample, you see some spots here, like this orange one with the purple or pink. They're not very separated, and the yellow and the purple are not very separated. So you go, okay, I'm going to choose another solvent, another organic solvent, where I have different partition coefficients. That means different affinity to the mobile phase versus the stationary phase. And then I take the paper and flip it clockwise, 90 degrees, and then put it in another solvent and let it develop. Then I get those spots that did not separate, they separated better. So two-dimensional chromatography, whether it's paper or column or even gel electrophoresis, which is not chromatography, you can get further separation. So the purpose of two-dimensional is for further separation of your constituents. Okay. So in order to compare your different components of your sample, there's one measure, which we call it the relative mobility of your component. And it's the distance moved by the component over the distance moved by the solvent. So usually when you have your line where you put your sample and the top where you stopped the development, where the solvent reached the top of the paper, you take that distance. And that would be the distance moved by the solvent. And then you take the distance from the line where you spotted your sample to the middle of the spot. And that would be the distance that your component moved. So the ratio of that is your relative mobility. So these are supposedly constant. So that supposedly, theoretically, every time you run the same components, you get similar relative mobility. However, there are factors that impact the relative mobility. Thickness of the paper, how thick is the paper? The humidity in the chamber, the distance of the development, like how long it took the solvent to reach based on the height of the paper, and then the temperature, because with higher temperature, you have higher mobility, faster movement. So basically, in order to have good comparison, you want to run a standard and all of your samples potentially on the same paper, run under the same conditions, then you can do a comparison that way. So it's better than running it on one paper and then comparing it to another run on a different paper.
So RM stands for rapid mobility.
Yes, exactly. So the higher the RF, that means depending if you have water as your stationary phase, that means the less polar your sample is. If your stationary phase is not polar, the higher the mobility, the more polar is your sample. So depending on what your stationary phase is versus your mobile phase. Yes, relative to the front. Okay. Paper chromatography can also be reverse phased. As I said, you can impregnate with water or you can impregnate with an organic solvent and develop with water. So reverse phase is basically your stationary phase becomes your nonpolar and your mobile phase become polar. Stationary phase can be ion exchange too. So, you know, we say it's cellulose and cellulose has OH groups, right? It's made up of glucose and glucose has OH groups. So these OH groups can be derivatized, chemically derivatized, to carry a functional group that has a charge, an acid or a base group that carries a charge. Then you can separate based on the charge of your molecules, and then hence the ion exchange. Okay, I guess I answered this a couple of slides ago, but just to see if you grasp the idea or if you want me to explain it a little bit more. So if you have reversed phase, that means you have a stationary that is nonpolar and mobile phase polar. The most polar travels the most, the least polar travels the most. The RF value of the polar compound will be higher than the less polar one. What do you guys say? Sam? You said D? Yeah. Anybody else? Agree? I see nods. Yes, I see lots of these also on the chat. So correct. So you got it right. So it is the most polar would travel with your polar solvent, and therefore your relative mobility would be higher. All right then. Thin layer chromatography has similar principles to paper chromatography. However, it is much better than paper chromatography. Why is that? Because it's basically you have, instead of a paper that doesn't have very consistent particle size or thickness or distribution, you would have a gel, for example, mostly silica gel, that is systematically in the same thickness spread over an inert surface. So the inner surface can be glass or aluminum, for example, and you spread your silica gel using specific tools that would make a very thin layer and consistent layer. So we get better resolution. Now you're going to say, what does resolution mean? Resolution means separation, basically. So your components are separated better. That's simply what resolution is. They're resolved better or separated better. You're going to hear these terms. And especially this is going to be used, this term is going to be used when we talk about chromatographic peaks and resolution of two chromatographic peaks from each other. So you don't have an overlap, you have two separated peaks. So when we say better resolution, we mean better separation, clearer separation, because we have smaller and uniform particle size. So your silica particle size, for example, are uniform and they are smaller. The audio sounds what? The audio sounds weird over Zoom?
Yes.
Yes. I'm not sure what to do about that. It could be an internet issue. Hopefully in the recording it would be okay because I'm recording it.
I think it's an internet.
Huh?
I don't think that issue. It sounds like maybe your mic is. Did it move or?
The mic is internal to the computer. I didn't touch it.
Oh, you sound good now.
Okay.
I didn't do anything.
Good, you're good.
Huh?
You're good now.
All right. I'm sure it will be good in the recording too. So I'll try not to move a lot. Okay, So we talked about it being a better resolution due to the uniform particle size, and because of that, the separation is faster, and we get better reproducibility. That means every time you run it, you would have better relative mobility. You can do better comparisons. Okay. So usually, you can, well, not usually, nowadays, you can buy these plates already prepared for you. In the past, many years ago, when I was a student, we used to prepare the gel ourselves and clean the glass, the square glass, and then spread the silica and let it dry and then run our samples. Now you can actually buy them and you can get the silica or alumina or cellulose. But the most common is the silica covered uh, plates. And you can get the plates mostly now plastic, but you can also have the glass or I think mostly aluminum foil is what you find. And then this, you can apply or run it as adsorptive. That means you can directly use the silica, for example, as your stationary phase, and the interaction will be based on polarity. Or you can have a normal phase or reverse phase partition where you impregnate the silica with water, for example, and it'd be normal phase, and then you will have a nonpolar mobile phase. Or the silica also can be, functional groups of the silica can be derivatized to carry a charge. Then you can run it as ion exchange. Same thing, you would spot your sample and then you would develop it in a developing chamber and then you let it dry and then you need to be able to see your components. So depending on what you're trying to separate, you can spray with anhydride if it is amino acid based. You can spray with sulfuric acid. The sulfuric acid will burn the organics and then you would see like a brown color where you have a spot. Or you can have iodine vapor where you also get color. Or you can have a fluorescent like dichlorofluorescein where you can see measure fluorescence. So basically, if you can do quantitation by measuring absorption or emission of radiation, or you can label your components and then measure radioactivity of these different compounds. You can take the density of the spots. So the more concentration you have, the denser is the spot. And there's a program where you can actually measure the density. You put your plate and then for the density to be measured. Now the name of the equipment is not coming to my mind, but you can measure the density. And then you can also take that spot out of your silica gel, and to get rid of the silica and just get the compound, you can run it through a small column or a syringe that is packed with a material or adsorbent that would absorb everything else other than your component. And then you can take it out, collect it, and then do more quantitative measurement on it. All right. Any questions on planar chromatography before we move into liquid chromatography? Column liquid chromatography. Okay, so in column liquid chromatography, we have two types. We have low pressure column chromatography, and we have high pressure column chromatography. In low pressure column chromatography, it's mostly a preparative. That means you run your sample and you run a lot of high concentration of the sample in an attempt to separate and collect enough amount for further analysis. So we call that preparative or semi-preparative chromatography. High pressure liquid chromatography is when your column is packed with your stationary phase under pressure, under high pressure. And this is mostly used for analytical purposes, where we are looking to separate compounds from the mixture, detect their presence, identify them, and quantitate them. And usually the columns that are packed under pressure, they give you better separation, resolution than low pressure liquid chromatography. So what I have here for you is to show you that column chromatography can come in different sizes, the columns. This is low pressure column chromatography. So they can be very, very long. Actually, there are columns that are on an industrial scale, where, for example, Agricor produce whey protein isolate using column chromatography. So you can imagine a column on an industrial scale. And so they can vary in length and in width, okay? And the bigger the column, the more material you can load on the column and the more material you can collect from the column. And the longer the column, the better separation you get. You're giving your sample enough time to go in and interact with the stationary phase and get better resolution or better separation. Same with thinner or smaller diameter. So smaller diameter, longer column, better resolution. And I'll talk more about resolution, not next lecture, the following. So they come in different sizes. So that's low pressure. This is the high pressure one. You'll see it in the lab next week when we run HPLC. This is high performance liquid chromatography column. So it's packed under pressure. The particle size are very small, well-defined, and there are no gaps between the particles, or the gaps are very, very small. So your resolution is very good and your peaks are very sharp. Okay, so you have really sharp, they don't have a lot of diffusion. You don't have a lot of like widening of the peak due to diffusion and due to empty spaces. You have it well packed with very small empty spaces between the particles. So we'll talk about HPLC next week. But let's understand a little bit column liquid chromatography setup. So what you see here, I'll try to use my cursor so that everybody can see online instead of me going to the screen and then you lose my voice. So what you have here, where is it? Okay. So what you have here is your column. And then we do have a low pressure pump that is used to pump a mobile phase onto the column and run it through the column. And we can control the rate of how fast the mobile phase is moving. That means how many milliliters per minute I'm pumping onto the column. And then sometimes I use 2 mobile phases, sometimes 3, sometimes 4, sometimes 1. And that brings me to talk to you a little bit about isocratic versus gradient mobile phase. So when I say isocratic, that means I have one mobile phase that doesn't change in concentration, okay? So it's just the same mobile phase going through until your run is done, throughout your run. You do not change it, so isocratic. A lot of things we do isocratically, we don't change. For example, a lot of the size exclusion chromatography is done isocratic. You don't change the mobile phase concentration. But oftentimes, many, many times, we use something called gradient mobile phase. That means the concentration of your mobile phase is changing over time. And this is often used to speed up your separation. Remember the example of buying something for the little girl to get out of the store. So here I'm changing the concentration of the mobile phase so that the compounds that are attached to the stationary phase and don't want to leave in a reasonable amount of time get out faster after the separation has been achieved. Okay, so to do a gradient elution or separation, so you sometimes have two mobile phases. Sometimes you need a third or a fourth, depending on how you're changing the concentration over time. Sometimes you need 2 different organic phases or 2 different salt concentrations. So anyway, let's think about it simple. And think about it, let's say this is water, for example only. This is water, and this is an organic phase, methanol or acetonitrile, let's say. And whatever is in the column, let's say it is nonpolar, okay? Nonpolar stationary phase. So if I have water running through, that is, I have a reversed phase chromatography. I have water running through a stationary phase that is nonpolar. So my compounds are going to interact via nonpolar interactions with my column. Great. So the ones that are polar, relatively polar, they're going to move along fast, get separate faster and move along. The ones that are less polar, they would like the column and they will separate and move slowly. Okay, after they separate, I don't want to wait 2 hours for them to come out. I need to get my sample up. So what I do is something called increase the strength of my mobile phase. So I pump in the acetonitrile. I start increasing the acetonitrile concentration, then my very nonpolar compound will say, oh, I have some acetonitrile here. It's nonpolar, I like it. I will go and I'll move along faster. So this way I am increasing the strength of the mobile phase. But here's the common mistake or common misunderstanding is that increasing the strength can be in any direction, depending on your mode of separation. It's not always increasing the organic phase. Sometimes if you have normal phase chromatography, you start with a nonpolar mobile phase. Then to increase the strength, you add water. Okay, see that point? So it's not always increasing the organic phase. It is increasing the strength in whatever direction you have an interaction with the column. All right, so sometimes in ion exchange, you increase the salt concentration or change the pH. And sometimes the pH is a reduction in pH or increasing the pH. So anything you do to the mobile phase, you are increasing its strength so that your components that are interacting a lot with the column come out. And for the one last point here is when you're working with low pressure liquid chromatography, you're the one that packs the column. This, for example, the high pressure liquid chromatography, you buy it already packed. This is something that you would pack and you follow manufacturer's instruction, like they would tell you based on the media or the stationary phase, they would tell you how to prepare it, how to pack it, how much pressure you want to have in order to achieve a certain height and a certain amount of your media that would be well packed. So you would be given the instructions to do that. Yes. Yes, so the question doesn't matter if it's dry or wet. This is depending on the media itself. Mostly you form a slurry, which is you take your media that comes in a powder and you just add to it whatever they tell you, either a buffer or water or organic phase, whatever they tell you. Okay, good. Supercritical fluid chromatography, I'm not going to spend a lot of time here. It's just that it's a type of chromatography that is mostly used, and I'll point out to the third point here, that it's mostly used for nonpolar molecules that are not volatile and are not thermally stable. So instead of derivatizing them and using GC, you can run them through supercritical fluid chromatography. So if they're not polar, maybe they're not too suited for HPLC. And if they are non-volatile compounds and not thermally stable, they're not very well suited for GC. So kind of this is the middle ground for specific components. And the mobile phase is called supercritical because your mobile phase is CO2 under high pressure and temperature above the critical point for this gas. So it has a liquid characteristics under these conditions. So it becomes flowy as a liquid instead of it being gas. And sometimes you can add methanol to this liquid CO2 to enhance the polarity of the solvent a little bit, because liquid CO2 is very nonpolar. So with this, the good thing about it, it has high diffusivity and low viscosity. That means it moves really fast and you get really good resolution or separation in very short time. So it has this kind of advantages, reducing analytical time and having good separation. So the stationary phases usually are similar to those in high performance liquid chromatography, which we'll talk about later on. And the equipment, that means the detector, for example, no, the equipment is similar to HPLC, but specifically the detectors are similar to those that are used for GC. And Gary is going to go over the different detectors that are used with the GC. Couple of common one is FID, flame ionization detector, and thermal conductivity detector. So these are common GC detectors, but there are so many others that Gary will talk about when he covers his GC lectures. So here's where we dive into mode of separation. The question that we had earlier was the difference between type chromatography and mode of separation. So here we're going to talk about within liquid chromatography, specifically liquid chromatography, what are the different modes of separation that are based on physicochemical characteristics. So the physicochemical characteristics of your stationary phase, your components of interest, and then the mobile phase that you're using. So I'm going to remove this chat box here. I can't see how to remove it now. Yeah, except I can't see the corner very well. Here. Okay. All right, so at the top, there's a differentiation between adsorption chromatography and partition chromatography. Adsorption chromatography is when you have your components adsorbing directly on a solid surface. So your stationary phase is solid, and it's adsorbing via specific interactions. These interactions can be ionic. So ion exchange is a form of adsorption chromatography. So it could be ionic adsorption. It could be affinity chromatography. And there's another one, which is hydrophobic interaction chromatography, can also be under the adsorptive chromatography. So, and then the other one, which we talked about, is partition chromatography. You have your inert solid and you have your liquid bound to that solid, and that liquid is now your stationary phase, and then your solute is dissolving in it and partitioning between the stationary liquid and the mobile liquid phase. And this separation, this solubilization is based on the polarity of your mobile phase versus the polarity of your stationary liquid phase. All right, so in adsorptive chromatography, that is ion exchange, you can see here the example. You have a functional group that is positively charged on your solid stationary phase, positively charged. That means your compounds that are negatively charged will be attracted to your compound. Okay, positive attracts negative. So you're attracting negative ions. That means other words for negative ions are anions. So you have cations and anions. Anions are negatively charged. So when you have a stationary phase that has a positive charge, then it is anion exchange. Why? Because it's exchanging anions. And that's another common misunderstanding or mistake when students hear anion exchange, they think the stationary phase is negatively charged. But no, it's positively charged because it's attracting negative ions. So hence we call it anion exchange chromatography. And then if we have the opposite, if we have the stationary phase has negative charges, it's attracting positive ions, then we call it cation exchange chromatography. So when you study, if you simply look at this here, anion exchange resin, since only anions can be attached to it, then this will remind you that it's the opposite. Positively charged means attracting anions, and hence it's called anion exchange. So when you study, do look at this figure here, then it would stick more better in your mind. So the next form of adsorption chromatography, here illustrated in this figure, is your affinity chromatography. It's like affinity, think about antibodies and antigen. So they're very, very specific, or enzyme and a substrate. Very, very specific type of interaction, not covalent. If the interactions are either polar interaction, electrostatic interactions, or hydrophobic interactions, or hydrogen bonding, or van der Waals. So any type of non-covalent interaction that is very specific between a functional group the functional group is covalently linked to your solid phase. This is covalently linked, but the component interacts very specifically, but not covalently with this ligand, we call it, or this molecule that is attached to your stationary phase. That is a very specific type of interaction, very high affinity. That's why we call it affinity chromatography. And we'll talk about it more and talk about examples later. The last one I have here in the figure is your molecular exclusion chromatography, or it's the same as size exclusion chromatography. Sometimes you also hear it as size filtration or size permeation. So they all mean the same thing. So molecular exclusion chromatography is similar to size exclusion chromatography. So basically you're separating based on the size of the molecule. So what you see here, you have a very complex kind of matrix that has different pore sizes. So your matrix has pores in it, and then your molecules will go through the pores and leave the column that way. The smaller the molecule is, the more pores are accessible to it. So it would go into almost any size of the pores. So it would be more detained, or what do you call it? It will be delayed because it's going to go into all of these different pores of different sizes. The large ones, however, will have only access to particular pores of larger size. So it won't go in and get lost in the pores. It will just move faster. So in size exclusion chromatography, we're separating based on size and kind of like filtering them. So the larger ones will just move faster because they don't go into all the pores, and the smaller ones will come later. So in a chromatogram for size exclusion, the large molecular weights will come out first, followed by the smaller, and then the smallest. Okay. Where am I? Okay, I guess this is a good stopping point. Since it's time already, we'll pick up on Monday. Gary will be lecturing Friday and then Wednesday because he's traveling. So we'll continue. Oh, sorry, don't leave, nobody goes. I want all of you to make, to form groups for next week's lab. So we need to form groups of 5. except for Wednesday, we will have a group of 6. So those of you that are online, if you know who you want to be partner with, you can form your groups and send me an email with it. I need at least 5 people per group. So you're here now, you can look around and see who you want to be partnering with and make sure you have, and just make up, one of you can email me with the pot. Who's in that pod? Okay, I need this by Friday maximum morning because I want to send you an email because each group will have a different lab that they're doing. Some of you will be doing GC, some of you will be doing a HPLC. So please send me an email with that. You can take a few minutes, and those of you online, you can privately chat with each other. Yes, Stephen. Oh yeah, definitely the Wednesday, the lab, Monday lab group together, Wednesday lab group together, because you'll be in the lab together. Thank you, Stephen. I should have said that, but okay. Huh? You're on Monday? Okay, so those of you on Monday, just stay, see who was on Monday and see if you can figure out the group. If not, email me and I'll put you in the group. Just put you in a random group? Okay, all right, sounds good.
So I guess I might have misinterpreted the slide, but is ion exchange and affinity chromatography an example of absorption?
Yes, that is correct. Let me stop recording here really quick. Ah.
Sure. Okay. Sweet. So you're
Oh, where is my cursor? Oh, here's my cursor.